In this video we're going to look at connected rates of change. Really quite a straightforward topic, but it always seems to puzzle people. Now I want to take you all the way back to primary school or early secondary school when you first learn how to multiply fractions. If you're faced with something like 3/7 times 7/8, the way most people do it is to say that 3 times 7 is 21, 7 times 8 is 56. And then, we'd better simplify that. Take a careful look at both numbers. 1 factor of 7, 21 divided by 7 is 3, 56 divided by 7 is 8, and the answer is 3/8. That's a real hassle, going towards these bigger numbers and then having to simplify. A much brighter idea is to recognise that because multiplication can be switched around, 3 times 7 is the same as 7 times 3. This is exactly the same thing as 3/8 times 7/7. It's exactly the same sum. And we know well enough that 7 over 7 cancels. And so the answer is just 3/8. But perhaps we can write even less than that. Let's try it one more time. 3/7 times 7/8. Now that we know that we can do this, we can actually say 7 goes into 7 once, 7 goes into 7 once, and the answer is 3 times 1 in the numerator, 1 times 8 in the denominator. And we've got our answer that quickly. It's far better. Now consider that for a moment, and let's try to approach it from a different point of view. Suppose I make up some random fraction, I don't know, 5/9. And I want to make a sum which multiplies to make that answer of 5/9. It's really straightforward. All I have to do is make sure that there is a 5 somewhere in the numerator and a 9 somewhere in the denominator. And then I can fill in all the other gaps any way that I like, as long as I pair them up. 17 over 17 is 1. 23 over 23 is 1. 57 over 57 is 1. This horrendous looking sum will definitely have an answer of 5/9 because I've set it up so that they will all cancel. I can do it with letters as well. X over y equals something times something times something. Make sure there's an x in the numerator, make sure there's a y in the denominator, and put whatever I like into the other positions as long as they pair up so that they will cancel later on. Now, we're going to use that idea a lot in connected rates of change. Let's take a look at an example. The side of a cube is increasing at a rate of 5 centimeters per second. Find the rate of increase of the volume when the length of the side is 3. Now, you need to do a little bit of detective work. This word, rate, it appears a couple of times. Rate, and over here, rate of increase. That word rate always describes a change. And if you stop and think about it, a change can only happen if time is going past. If time wasn't going past, then nothing can change. So you see this word rate, and you immediately start thinking something dt, simply because time must be involved. There's another clue in here. Per second. That per second shouldn't surprise you because we've got over time. Now, we need a letter to represent the length of a side of a cube. You can use whatever you wish. I'm going to use x. So the side of a cube is increasing at a rate of 5 centimeters per second. This is dx by dt. You can see it in the sentence, you can see it in the units, centimetres per second. This is all measured in centimetres per second. And dx by dt therefore equals 5. Find the rate of increase of the volume. Well, that's going to have to be dv. So we've got dv by dt, we've got dx by dt. Using what we saw at the beginning of this video, we're now going to try and put all that together. We are supposed to work out the rate of increase of the volume. How can we make that happen? Well, connected rates of change. We must have a dv in the numerator, we must have a dt in the denominator. And we can put whatever we like in here as long as they match, so that they effectively cancel out. Now the only other thing that we've got going on is this dx. So that's going to be dx, and that's going to be dx. Notice I didn't write it out from left to right. I wrote out the things in the order that I was thinking about, which is why the dx's were written last. Now, some of that is straightforward enough. Find the rate of increase of the volume. dv by dt is what we want to know. dx by dt is 5, so I can put a very easy times 5 in there. It's this rate of change which is the puzzle. We need to come up with some sort of statement for v in terms of x. So you go back to your most basic general knowledge in maths and you start thinking about a cube. Not a cuboid, but a cube. We know that a cuboid has a volume equal to length times breadth times height. But a cube has all of the sides the same length. And so for a cube, and using the x, the length of a side of a cube that I introduced at the beginning, the volume of a cube will be x cubed. And I've now got a way of having a statement for this. dv by dx, very simple, equals 3x squared. So I can take this and I can substitute it in there. dv by dt is 15x squared. Now, we've got this. We're interested in dv by dt when the length of the side is 3 centimetres. A lot of people fall into the trap of using this near the beginning of their working. I think they look at it, they think it's a nice easy number, they want to start somewhere easy, they start with the 3. A bad mistake. Leave this very simple looking statement until you're pretty much finished. At x equals 3, so at the moment when the side length is 3 centimetres, then dv by dt is 15 times 3 squared. 15 times 9, 135. Now, there is a little bit more to say about this. Come back to the units. We saw at the beginning that dx by dt was measured in centimetres per second. You need to have similar thoughts with regard to all of these. Here we're going to have centimetres cubed per second. Here we're going to have centimetres cubed per centimetre, a slightly strange thing. There we go. And centimetres per second, as we saw already. So volume, time, this is centimetres cubed per second. And that is connected rates of change.